Hey everyone, in this video we will see how to solve ODEs in Python. Now ODE stands for Ordinary Differential Equations, and basically, to make it short, it is a equation that links a derivative with its function, for example. Prepared some examples, but before we see the examples, we are going to speak about the two functions you can use to solve ODEs. Now the two functions are the scipy.integrate.odeint and then the scipy.integrate.solveIVP. Now IVP stands for Initial Values Problem. There is another function called the BVP, which is Boundary Values Problem. But in this video we will just see the IVP since we will be dealing with Initial Conditions Problem. Now to install scipy, very straightforward. You do a pip install scipy. I already have it installed, as you might have guessed from my previous videos. Right, so everything is satisfied. I clear everything. Let me hide this. Now, what are ODEs? ODEs is a mathematical equation that links a function y to its derivatives. Now, it can be the first derivative, the second, third, up to the n term. Now, the term ordinary signifies that the equation involves derivatives that only has one variable, for example, time or space, t or x, for example. Now we have multiple examples of differential equations. For example, here we have the Malthusian growth model, where n is representing the number of individuals, and r is a growth rate. Same goes for Newton's law of coding, where you have dt over dt is equal to k times c minus c ambient. So you have different types of equations. The simple harmonic motion of the mass spring system, remember? We dealt about this equation in a previous video. The equations can also be non-temporal. For example, all the mathematical equations you deal in calculus or any math class. There is two main type of ODEs. They can either be initial value problems or boundary value problems. The initial value problems will identify... So you take your ODE, right? Let's say it's the second order. How do we know it's the second order? You just see the term that has the highest derivative. For example, here it is y2, so the order of this equation is the second order. Now all the elements before that second order, so the first order and the zeroth order, have to be identified at t equals 0 or x equals 0 or any initial condition. For example, here we have y0 is equal to 1 and y prime of 0 is equal to 0. Now we also have the boundary value problems, but this will not be the subject of this video. But it's also very straightforward. It's almost the same thing. Now, what is the logic behind solving ODEs numerically? Now here I prepared a little example, but let me explain it to you first with the oh so good Paint software. Now you see here we have a function y. This function y evolves across t with a certain rate. We don't know the equation. For example, it can be... Consider this very simple equation where dy over dt is equal to y. Now we have the initial condition right here. So at t equals 0. So this is our initial condition. What we want to do is know how this function y will behave across the time span between 0 and 10 seconds. Like, will it go like this up, or will it go down? Then will it oscillate, for example, or is it an exponential like this? This is what we want to know. It's the evolution of this y entity. Now let me clear all of this. Numerically, we are at t equals 0. Now logically, we are doing something numerically. Whenever you see the term numeric, you know that a continuous space will be transformed into a discrete space. So this time span between 0 and 10 seconds will be divided into minor, like a grid. Like so, where this is t0, this is t1, this is t2, t3, t4, all the way up to here, tn. This will be tn, and this will be t0, right? Now, we are at t0, we want to go to t1, then t2, all the way up to tn. To do so, we have to evaluate the point y1. So we don't know what y1 is equal to, and something we are looking for. Do you remember the Euler method, for example? Or solving differential equations numerically in general? There is one trick you can use. You see here this derivative. we know that this derivative can be approximated with, for example, y1 minus y0 over t1 minus t0, right? Yeah, this is the classical slope calculation. We all know that. Now, something interesting now, let me change the color. This here can be represented as dt, so this is delta t, and this here, y1 minus y0, can be written in the form of y1 is equal to y0 plus dt times this derivative right here. So if I go back to my Visual Studio Code, you can see here we have s1 minus s0 over dt is equal to ds over dt, and then s1 is equal to s0 plus dt times ds over dt. What we just did right here is finding an expression for s1. We have s0, this is the initial condition. Now, we are looking for this dy over dt, something we don't have. But remember, we have our differential equation, this one, that says that dy over dt is equal to y. Now, dy over dt at t equals 0 will be equal to y0. So we know that, coming back here, that s1 is equal to s0 plus dt times ds over dt. Now we know that ds over dt is equal to s, by analogy to our equation right here, which is equal at t equals 0 to s0. So, in a way, we found a way to express y1. Now we have y0 and y1. We want to get y2. We do the exact same thing with y1 and y0. And then we repeat that for y3, 4, 5, 6, 7, etc. until we reach yn. By doing so, you'll see that we get our dots from 0 to 10 in a discrete manner. Now we saw the process of solving ODEs numerically. Now when it comes to the Python function odeint, it has the following arguments. So if we go to the reference right here, we can see that scipy.integrate takes all of these parameters. Most of them are not very relevant to us. Now the relevant inputs will be the func. Func is a function that defines our system of ODEs. It computes the derivative of y at t or y at x. We have our initial condition y0, so here they call it y for some reason, but this is just a vector of initial conditions. We have the time points in which we want to study the problem. So this can be either t goes from 0 to 10 seconds or x goes from 0 to 10 meters, for example. Now keep in mind that when you use odeint, this t parameter has to be monotone. So if I come back here, now the t array is a sequence of time points for which to solve for y. Now here they say that the initial value point should be the first element of this sequence, monotonically increasing or decreasing. So in a way, repeated values are not allowed when you use odeint. So your time points have either to be continuously decreasing or increasing. Now, the fourth parameter that is relevant to us is the arcs. So this represents all the constants. Rtol and Atol stands for relative tolerance and absolute tolerance. So this is in a way to control the errors and the precision of the solution. And then t first is an argument that we'll discuss about it. It is a Boolean that can take either true or false. Now let's see by solving this very simple equation called the Malthusian growth model. So this equation describes in a way that, for example, you have a given population at t equals 0. Let's say you have 10 people. And then you can say that r is a growth rate. For example, every year, this population increases with 3 people, for example. Before we can solve this system, I want to speak about something very important when it comes to solving ODEs in Python. Now you see, Python is a programming language. It takes zeros, ones, makes some operations on these, and returns 0 and 1s. It is not like math where you have abstract symbols and everything. Now, when you want to solve ODEs in Python, you have to, in a way, package your problem properly and frame your problem. How would you do so? You have 3 steps before you can solve something. You have to first arrange the terms of your ODE where the highest order derivative is on one side and all the rest is on the other side. For example, here we have the second derivative of y plus 2 times the first derivative of y minus 2y is equal to 0. We take these terms, put them in the other side of the equation, so that we have just the highest order derivative in one side and all the rest in the other side. Now that was step 1, which is arranging the terms of your ODE. The second term is identifying the initial conditions of your problem. So if, for example, here our highest order is 2, then we will have 2 initial conditions on y and the first derivative of y. For example, here we have y prime of 0 is equal to something and y of 0 is equal to something. And then the third thing to do for framing and packaging a problem is to identify the interval in which you want to solve your ODE. Now we know that it should be a discrete interval, that's for sure. It can be spatial, temporal. You often see that in the ODE function here, we speak about t as in time, but you can also use x, for example, to describe space. For example, t goes from 0 to 10 seconds across 100 points, or x goes from 0 to 1 meter across 100 points, which you will define with numpy, by the way. Alright, now that we discussed that, let's go back to our problem here. Our Malthusian growth problem. Now, when you want to solve ODEs in Python, I describe them in 3 easy-to-do steps. First of all, you define the constants, time points, and then initial conditions, and every initial variable, let's say. So here in our problem, you'll have n0, which stands for the initial number of individuals we have in our model. So for example, we have 10 individuals. R is the growth rate. So let's say that each unit of time we get 3 new individuals. So let me do, now we define both constants n0 and r. And the third thing is the time points. It is the interval in which we want to study the problem. Let's say that time points is equal to np.linspace from 0 to 10 seconds, let's say, across 1001 points. This means that we will generate an array starting from 0 all the way up to 10 and then across 1001 points. Alright, so this was first step. Now that we define all the constants and the variables and the initial conditions and everything, the second step is to define our function that characterizes our system of ODEs. Now, this function right here will be then inputted into this ODEin function. So I will do like this. And to speak about this function right here, if you go to the official scipy documentation, you see that this function right here, so the first parameter right here, is a callable y and t, or callable t and y. We will just speak in a second on what this is about. Yeah, this function computes the derivative of y at t. So if I come back here, this function computes the derivative of y at t. This means that it takes as input a vector y, a vector t, and some additional arguments representing here. To define this equation, we have r, we have n, that's all we have. Right, so this function, we can say that n is equal to y. And then we have the constant r of our problem, so we can specify it right here. So r. And then this function, remember, turns the derivative of y. It returns our ODE. And if we see here our ODE, r times n is equal to dn over dt, which represents our ODE right here. So we do a return r times n. Or you can be a bit more fancy and do it dn dt is equal to r times n, and we return dn dt. Okay, very good. In this ODEin function, remember, we said that it takes a func, y0 to state the initial condition, time points, and arguments. Alright, so let's specify them. We have our function right here. It takes initial conditions, so for example, y0 is equal to n0. Okay? It takes time points, for example, t is equal to time points, and it takes additional arguments which represents the constants of our problem. It can be a tuple, for example, if you have multiple arguments, for example a, b, c, etc. But since we have only one, we will specify it as r. Now this should be everything we need to solve our problem, so let me run this. It ran, let's print the solution. Right, we get this array right here. So this array represents the solution of our problem. So n at t equals 0 all the way up to n at t equals 10. Let's actually plot this one right here. Now I did here a very basic plot of the time points with the solution. If we run this code, now you see here we have this solution right here. This seems rather an odd solution. You have then 0, 0, 0, 0, and then up at 10 it's e to the power of 14. Well, this is actually normal, because if we go back to our equation right here, the solution of this equation, if you solve it, gives n of t is equal to exponential of r times t. Now r is equal to 3, and then t will be equal at 10. If you compute it exponential of 3 to the power of 10, you'll see that it is. So let's actually reduce it. Let's say that each unit of time, instead 0.3 new individuals each time. Okay, let's rerun the code, and let's display this. Now you can see here, we start at 10, and then at t equals 10 seconds, we have 200 individuals. Alright, so that's pretty interesting. Now let's say here, you don't want to call the y vector first, you want to call t. So let's do t, and then y. If you run this, you have to specify here that the first argument, so t first, is equal to true. This will in a way tell the function that here the first argument is in reality the time points. So t first, logically, is equal to true. And if I do, for example, here, y and then t, logically, this will be false. Alrighto, very good. So this concludes our example for the first order ODE. Now for solving higher order ODEs, it is actually the same principle. If you understand the first example, this one is also very easy. You see at a second order ODE, we have S0, then S prime 0 at t equals t0, and then we want S1 and S1 prime at t equals t1. It is exactly the same process, just that S1 prime minus S0 prime over dt is equal to the second derivative of S. We get S1 prime, and then once we get S1 prime, it will be exactly like this scheme right here, where we can compute S1, and then so on and so forth. So it's exactly the same principle. We can consider another example of the harmonic motion of a damped mass spring system. So again, here, we define the constants, initial conditions, and time points. The constants of our problems are m is equal to, let's say, 1 kilogram. The damping factor is equal to, I don't know, let's say 0.7, I think. And then k, the stiffness, Newton per meter. Now let's call the initial condition. So call it initial. We have to have initial conditions on here S0 and S prime 0. So in a way on x0 and x prime 0. So this will be a vector of two elements. For example, this is x0. It is equal to 1 meter at t equals 0. And then x prime 0 or x dot 0 is the velocity at t equals 0. It is equal to 0. Then we can define the time points. So time points is equal to np dot length space between 0 and 10 across 1001 points. Now remember, we have to frame our problem in a way that we have to make the higher order term in one side of the equation and all the rest of the terms in the other side of the equation. So let me actually change this. So this will be, alright, so it'll be like this, where we have the second derivative is equal to minus b over m times dx over dt minus k over m times x. So I just brought these two elements in the other side and then divided by m. So this here will be passed to our function that computes the derivative. Remember, it is this function right here, system of ODEs. Now you can see here that we have a vector x dot, and then k, m, and b. So we specify here our vector y, our time points, and then some constants which are m, and then b, and then k. We extract the values from this vector y here. So this will be, for example, x and x dot is equal to y. And then we compute x dot dot. So let me call it x the dot is equal to this equation right here. So it's minus b over m times x dot minus b over m times x dot, and then minus k divided by m times x. Okay, and then we return x dot dot, x dot dot. Very good. We fully define our function right here. Remember, this doesn't depend on t as well. It's not very much a problem, but remember, you have to specify this argument right here. In our function ODEint, we pass in our system of ODEs. We specify the initial conditions, so y0 is equal to initial conditions. Okay. We specify the time points, t is equal to points, and we specify the arguments that are equal to, they have to be in the same order as these ones. So it's m, b, k. Okay, now this is our, let me call it solutions. This time you will see why. If I run this code. Alright, so it gave an error right here. It says that the size of the array returned by func1 does not match the size of y0. Alright, so this is actually my bad right here. We returned x dot dot. So this is a one-dimensional array. But you see here our y is a two-dimensional array. We do have a higher order ODE. Okay, for example, here we have the second order ODE. Our array S should contain this function right here should return the second order term and the first order term. Why? Because here you can see that we used it to compute S1 prime, but then we are going to need ds over dt to compute, here, S1. So we need both ds over dt and the second derivative of s over t. Alright, so let me just fix it right here. I return x dot and x dot dot, and I return x dot. Okay, now everything should work. Alright, so we have an array right here. So it's a 2 by n array. So this represents x0 and then x0 dot. This is x1 and then x1 dot. And then this is x2 and then x2 dot, etc. Now to get the separate arrays x and x dot, it's actually very simple. X solution is equal to, and then x dot solution is equal to. Now remember here in the x solution, it's the first column of all the rows. It's the first column of all the rows. So all the rows across first column. And then x dot solution, oh, this is 0. 0 represents the first column, and then 1 represents the second column. So if I go ahead and print x sol, so you'll see that we get this time an array. I think here we have to first start with x dot and then x dot dot. I'm not sure. Yeah, this was my bad. Naturally, you return first the lowest degree and then the higher degree. Alright, so this was my bad. Okay, so it makes sense. Actually, it makes sense. If you have an array, let's say of y. When we return something, you see here, we return x and then x dot. And then the derivative of them should be x dot, which is the derivative of x, and x dot dot, which is the derivative of x dot. Alright, so it makes sense. Now here we have our solutions. You can see that, let me omit this, we run the code. So this is the position of the mass. You can see that the system is damped here. It starts in an initial position of 1, and then it slowly is damped. Alright, so the same goes for the speed. Okay, alright, so very good. We saw how to solve a first order ODE, a second order ODE with an initial value problem. Now the last thing I want to speak about is how to solve a system of ODEs. This is actually the whole heart of this function right here. I already dealt a problem related to the double pendulum in Python. So basically, to gain some time, it's actually the same principle right here. So this is our function. Now if you have a system of ODE, for example this in the double pendulum problem, it's actually the same principle. You have two equations. For example, this is the first equation and this is the second equation. Now there is terms in this equation that appears in this equation, and so it's a combination of the two equations. Again, what you need to do is to form, for example here in the case of theta, the second derivative of theta 1 is equal to something, and the second derivative of theta 2 is equal to something. And then it basically is the same principle where you have some initial conditions. So these two first conditions represents the initial condition of the first system, and these two are the initial condition of the second system. We define the constants. Here we have our function of the system of ODEs. Again, you see here, this is the vector y having the same shape of the initial conditions. So, and then you have our first equation, our second equation, and then we return the theta 1 dot, theta 1 dot dot, theta 2 dot, and theta 2 dot dot. And then it is exactly the same thing. You extract the solutions. If you understood this very basic example, you can build up to solve second order ODEs. Example here. For example here. Now if I add, for example, another set of initial conditions right here. So this is for the first system, second system, let's say. And then here we have x1. So x1 dot. And then I have x2 dot. For example, x1 dot, x2 dot. Alright, you do this, and it's basically the same thing. Now here, if we omit this and print solutions, you'll see that now we have an array of 4 times n, where the first element is the, here, represent, for example, the displacement of the first system. This represents the velocity of the first system. This represents the displacement of the second system. And this represents the velocity of the second system. Now, if you want to challenge yourself, I highly suggest you to try solving the double pendulum in Python. It is a very great example to understand how to use the ODEin function. If you struggled with solving this example, I recommend you checking out this video to see how we can do it in Python. It is actually a very interesting example since it involves the ODEin function, but also some symbolic computation in the scipy and numpy. I very much detailed all the solution, so you will not find yourself lost trying to understand it, plus having some simulations with it. So, I hope you enjoyed this video. If you have any question, or something wasn't clear, or something was confusing, let me know in the comments. I very much highly value your feedback, and I hope to see you on the next video. Peace. Bye bye.